Um, Dr. Paul, I'm not going to hide my goal in life from you. I'm going to tell you right now. I want Nigeria to be the best country in mathematics as soon as possible. That's it. I'm not hiding it from you. I want the next Isaac Newton to come from my village. Okay, so now that's the context we've come from. Does that make sense? Amos is saying, if we put in the work, Dr. Meyer, can we make Africa and Nigeria specifically one of the best in mathematics by using AI to supercharge our learning? How can we leverage AI to supercharge learning for students in Africa?
That's a great question. The first thing I'll say is a lot of people in, at least at Rice in the PhD program, have a very high view of Nigerian PhD students. They're people that come and they're incredibly smart and hardworking. My fiance, her roommate was Nigerian, and my fiance had nothing but good things to say, like, wow, she's really smart, she's really committed. So I think that's absolutely possible. I would love to see the next Isaac Newton or Claude Shannon come from Nigeria, and I think it's great that we can make this happen. I think using AI to supercharge education is going to involve using AI, but using it in a very intentional sort of way. And this means using it not to do thinking for you, but using it to help augment your understanding or to help, prompt and fill in gaps when it's something you don't understand. Right now, for instance, there are a lot of people, they can ask AI to do certain coding tasks for them, and this idea of vibe coding, right? Where, oh, I'm just going to prompt AI, it's going to give me code, and I paste that in, and I never really understand what the code is doing. And I think to be the next, Isaac Newton or Claude Shannon, you have to know what you're doing. So where I see AI fitting into that picture is helping students along the way when they get stuck or when they get confused. Like, you write the code yourself, and then you get to a point where my code isn't working or it isn't putting the output that I'm getting. This is just a coding example. You prompt AI, and learning how to prompt AI is a really good skill to have, and say, here is some code. It's giving me this error. It's giving me this certain output. Why might this be, or why would this be? And then you paste your code, and it can actually do a pretty good job of, I guess, I try to qualify my language, because the idea of AI even having knowledge to begin with, I think, is a very questionable thing. But it can do this. It has access to, it's memorized basically billions and billions of text documents from all over the internet, and it can basically be like, the way I think of it and conceptualize it is, oh, somebody's asked a similar question. There's as it's pasting in the tokens for the response, it's basically pulling from other similar issues, so it can help a lot there. Prompting it to help understanding, like, what is an intuitive way to understand, say, Maxwell's equation, or Newton's second law, or give me some examples. Those are great ways to prompt AI. One of the ways I like to conceptualize education is, we have this kind of knowledge. We all have this base knowledge, and there's kind of this horizon of the edge of our knowledge. And when we learn new things, we're trying to connect what we already know, what we've experienced, what we've learned or memorized, to something new, to some new concept. And I can think AI can help in helping make connections between some new concept that we're trying to understand. We're trying to push the boundary of our understanding or our knowledge to something new. And that's where those analogies and other things can help. And one of the things that AI is so good at is the personalization aspect. You have a professor that is somebody who, they have their own background and their own way of conceptualizing, but some of these guys are like, they're older than us, and that's not a bad thing. That's really wonderful. They have a lot of wisdom, but they've lived, some of them, some of my professors, they grew up before the internet. They wrote their thesis on a typewriter. So where they're able to draw from might be different. So again, and this is especially useful when, say, if you're a Nigerian student, what are some of the things when you read work that's written by, say, Americans or British people? There's going to be connections, but there might be certain cultural things when you're reading a textbook that may not resonate as much. So I think the AI can really help in taking what you already know and help bridging that to something new that you're trying to learn.
Wow. So I didn't even give you a chance to introduce yourself. Sorry, I went to the crux of the matter.
No,
Um,
it's great. People are eager to ask questions. So
yeah. So I don't know if I should introduce you first, or should I say how we met? Which one should I do first?
You should say how we met. I think
Yeah.
that's fun.
So we met at Cambridge, for while we're there for colloquium. And I think that when we met, one of the things that stood out, first of all, I know we were on the same bus. So I landed in England, and a guy who I hadn't seen for about 10 years saw me and said, Amos? And I was like, who would know me randomly in a bus? And so then we met and we started talking. But then one thing that stood out to me from your time there, you knew what you were looking for, information theory, or you wanted to learn more about that and so on. But here's what's crazy and interesting, right? A lot of people on this call, by the way, love Dr. Stephen Meyer. I love Dr. Stephen Meyer. So anyways, I'm just giving that quick side note because I wanted you to know that they all love your work and these guys' work. So I bring that up because what is interesting is that when you ask the question about Shannon Claude, that is an interesting question. So please, I want you to introduce yourself, but here's what I want you to do. People on this call might have used an app called Claude, but they don't know where Claude is connected to. Why is it called Claude? Can you tell us a little bit about who is Paul Meyer?
Yeah, so let me try to think what would be a good place. So I'm originally from California, was born and raised in California, and I did my undergraduate at Rice University in Houston, Texas. I think at the time I was really debating between computer science and electrical engineering. And my big passion has always been music production, making music and the kind of more technical aspects of it. And at the time, I loved math, and math was like the thing I loved, and I wasn't sure if I should major in mathematics and other things. And people were like, well, electrical engineering is like the most math heavy of all the engineering. So if you like that, you should do it. And it's funny because when I was in physics, I hated circuits. I did not like circuits. And I'm like, maybe I would not be a good electrical engineer because I don't like circuits. But I still decided to take an intro electrical engineering class because people said, oh, it'll have a lot of math. And it had enough math for me. It was a lot of math. And what really made me fall in love with the field was the signal processing element. And that has a lot of connections to music because you think of audio. Audio is like a signal. It's some information that's encoded in, usually you'd consider it to be a voltage over time, and that represents the audio signal. But where that gets to be interesting is in signal processing and electrical engineering in general, where signal processing is like, processing signals, it kind of gets to be philosophical. Like, what is information or what is signal? And as you start you can kind of abstract beyond this and say, wow, like this can be anything. It can represent stock prices. It can represent, it doesn't even necessarily have to be an electrical signal. It can be like speech or things written down on a piece of paper. So that really kind of supercharged my interest in AI. I stuck around and did a PhD. My PhD advisor so I finished my undergrad in 2014, or sorry, no, 2018. I started in 2014, and I went right into a PhD program. A professor that I had as an undergraduate wanted me to come in. I originally was going to go to Princeton, but the guy, my advisor, who was my advisor, he was like, no, you should stay here. And he kind of gave me the sweet talking of why I should stay at Rice to do my PhD. And he's a very big name in the field. And right around 2015 to 2016, he's like, you guys need to learn AI. He totally changed the kind of the curriculum to add AI, and he knew it was going to be big. And he was way ahead of the curve, like right on the cusp of when it was starting to be big. And it was a really smart move on his part for us to learn it because I worked at Intel. I had a couple internships there, and I went there one summer and I'm like, hey, I want to work on AI. And they're like, no one's really doing that, blah, blah, blah. And then I go there the next 2 summers, and finally 2018, right before I started graduate school, I go there, and that's anything, that's all everybody's talking about is AI. So it's funny, like to be, a couple years ahead of when everyone else is doing it. But that's something we can talk about. What are the next big things that we see coming? So that's what I kind of did my PhD in, but it always, and this is something in our PhD group, we always have a strong background in the signal processing and the electrical engineering fundamentals. So we'll take that approach and use that to kind of either design new AI algorithms or improve interpretability. And I think that's a really important combination to have. So if you're interested in electrical engineering, that's if you still eventually want to go into AI. I'm a little biased, I guess, but I would say definitely go into that. And one of the things that was really cool, I'll just kind of as an aside, I got interested in philosophy, especially later on in my undergraduate, actually, because I don't know if some of y'all know John Lennox, but he came to our university and gave a talk, and he's a mathematician, and I think that really encouraged me to start learning a little bit more of the philosophy side. Claude Shannon's an interesting figure because he's the guy who's kicked off the field of information theory. He was a brilliant, brilliant guy. I mean, he's the one who did it. Now, what's really interesting about Claude Shannon, there's two pieces. He recognized the importance of mathematical logic, which is kind of a branch of philosophy, but it's also the way I think about it is this is the glue that holds together mathematics and philosophy. And Shannon realized this field of philosophy and mathematics is applicable to electrical engineering. So his master's thesis applied George Boole's laws of thought to the theory of switching circuits. And this formed the basis of the modern computer. And this was over a decade before the transistor was invented. He turned circuit design, digital circuit design, into a science before the transistor. And he recognized the relevance. So that was amazing. And then, you think later, that wasn't even his most, I mean, you could say perhaps that was his most important contribution, but most of us will say his most important contribution, and that, by the way, that paper was in the 30s, I think 1936 when he published that. But his most important contribution was I think it was a 1954 paper called A Mathematical Theory of Communication. And just like he had turned circuit design into a science before, this was the paper that basically quantified information, basically said, this is what information is mathematically, not necessarily philosophically, but here's how we can conceptualize and think about information mathematically. And this formed the basis of communication theory. So, and information theory. So anytime you send a text, anytime you use the internet, this is all based on the mathematics and the development of stuff that Claude Shannon made. So super, super influential figure, and somebody as double E's we really like. He basically, he's the father. I mean, Maxwell's the real father of electrical engineering, but Claude Shannon is like the guy who kind of kicked off the more modern form. And obviously he's standing on the shoulders of giants like Maxwell and George Boole and other people like that. But he was in the right place at the right time.
Wow. Wow. I think one question that comes to mind right away, who are the key names? And then let me tell you my theory, and then you can tie it with the names. I believe that if people want to go to top universities like MIT and Rice and so on, they should learn to think like some of the best thinkers have, like Newton. Like they should go solve problems and then make that an activity that they do, right? So if I love solving problems, I generally will become much better. And then when I apply, I probably have something to show them. Tell us a little bit about getting into top universities like Rice, students in Nigeria who want to go to Rice, whether for undergrad, maybe let's start with undergrad. How can they prepare themselves to be ready for that? And then, yeah, if you don't mind, maybe drop in some names of, other than Claude Shannon, who was exceptional, who are the other names that we should know if we really want to be excellent and exceptional at AI?
Oh wow, those are two great questions.
We
In
can start
terms
with the
of
first one, and then it's up to you.
yeah, I
Yeah.
was gonna say a few names that really come to mind. There's a guy from Stanford, Wigner. He's a very influential, kind of more foundational figure when it comes to AI. Nowadays, there are a lot of names. Like the biggest one right now that to be familiar with is the two that come to mind right now is Yann LeCun. I don't agree with everything, and Geoffrey Hinton. Two people, there are a lot of things I disagree with, but any sort of paper they're working on, anything they put out, great names to have. These are people, they're still alive, they're publishing now, and they were around. Especially Geoffrey Hinton, he's kind of the father, the godfather of the modern AI revolution. Wrote the paper in the 70s that kind of made that happen. But it's interesting to trace where AI went historically. I mean, there are names you should be familiar with, like Leibniz. You can trace the legacy of what we consider to be computer science now all the way back to Leibniz, and just realizing that there's a lot of people, Leibniz, Alan Turing, again, somebody you should be familiar with, even though I disagree with him on a lot of things. He was a PhD student of, Oh, the guy who did lambda calculus, and this is he's a great computer scientist, fantastic, really smart guy, Christian. I'm trying to think of his name, but it'll come to me. But those people, and then you look at their legacy. Eventually, people like Wigner and people like Jeffrey Hinton, and then to the modern day, you'd have Yann LeCun, and Hinton is still publishing. He's still having new ideas. So those are some of the names I would say to be familiar with. It's difficult because the field, those massive fundamental discoveries have been made. So it's hard, like Leibniz is kind of like the last universal genius in a way. But then you have people like Claude Shannon who are able to synthesize across disciplines. But anyway, in terms of preparing yourself, especially to get in at the undergraduate level, one thing that's important is to have a broad set of strengths. So obviously, when I was applying, and this was, more than 10 years ago, test scores were a big thing. If you wanted to go into more technical field, I think SAT scores were more important. If you were kind of more in literature, you could do ACT. You don't necessarily have to do both, but it's not a bad idea to do both because one may show your strength more than another. For instance, from what I understand, ACT math is easier than SAT math. So if you take them both and you look at you look at your ACT score, that's great. At the graduate level, your GRE, which is kind of like the SAT for graduate school, it's less important. But on the undergraduate level, because there's so many applicants, it's not bad to try to get the best standardized scores you can because people have an idea that high school in other places might be easier. And because everyone's taking the same test, the standardized testing is an important piece. Now, you don't have to have the highest score, especially if you're looking at, if you want to go into engineering or STEM, you don't need to have the highest reading and language scores. But what they're looking for is a certain baseline score to say, you can communicate, you can write, you can speak. And this is especially important if you're an international student, you're wanting to come to the US because there's, again, it's not a fair perception, but there's a perception that will this person be able to understand and do it. So a lot of the Chinese students, for instance, they'll have to take the kind of the foreign language test, but then also universities will look at their language requirement. I'm talking a lot about standardized testing. It's not the most important, but it is very important. And I do encourage doing subject tests. Like if you can say doing like mathematics, especially if you're interested in STEM, doing the mathematics subject test and having a good score on that, that's going to help you because it's like you took the normal SAT, you got a certain score, you did the SAT math, you'll get a good score. If you can get a good score on that, then that's great too. And it's okay to take it multiple times. They'll composite your score. They're really only looking at your best score. I never took any SAT prep classes or anything like that. I did do well on the math and the math subject test. So try to do well on it. I would say maybe it's worth doing a subject test or just doing it once or taking a practice test under the real conditions that you would have. So set a timer, do it like you would, and then look at your score and say, is this something I need to do some work for to get myself up to a certain percentile to show that I'm a competitive student? That's a big one. Obviously, grades from high school are important. They're very important. One area that's become less important over the last 5 years has been personal statements. Now, you should definitely invest as much as possible into doing a good personal statement, but with all this AI and everything like that, people have kind of realized that people can hire people to write personal statements for them. There's a lot of kind of issues that can come about from that. So what I would say with your personal statement, and here's part of the problem, the application process. These universities like Rice and Stanford and MIT, they get so many applications that there's some randomness, there's noise in the application process, and it can just be who's reading your application and how are they feeling that day. So if you don't, obviously, if you don't get in, it doesn't mean that it's not a perfect process. And obviously, for all of you, you should never take a rejection from a university as a rejection of your own worth or your intelligence or anything like that. I didn't get into, and there's political elements of this, and I mean more like geopolitical. The university I wanted to go to as an undergraduate was Harvey Mudd. I applied early decision, didn't get in, but I got into Rice. Harvey Mudd is in California, Rice is in Texas. I'm from California. So schools will want to show that they have a lot of students from out of state, makes them look more desirable. Rice actually offered me a fee waiver, so I didn't have to pay to apply. So they looked at my either my subject test or my pre-SAT score, and they said, we want you. So that's another thing, right? If you do a subject test or you take the SAT, the pre-SAT, and you do well, schools will reach out to you. And if they give you a fee waiver, there's a good chance they would admit you because they think you're a strong candidate. So that's something to look out for, and that's something that can come about from doing these tests. So as much as we hate standardized testing, I'm sure many of you hate taking tests, it is an important piece of the process, fortunately or unfortunately. And I say fortunately because to me, it's more fair. People have found that, yeah, people who are wealthy can pay for test prep, and that is true. But people who are wealthy tend to go to schools or private schools that have more grade inflation. So especially in the US, you have these private schools where everyone gets A pluses, or, a lot of people do. So colleges are getting privy to that. But anyway, I'm digressing a little bit. We were talking about just kind of random. Sorry, go ahead. Amos, you look like
Yeah,
you
so
wanted to
how
know.
do you so then what about like a project for like somebody who is in seventh, eighth, ninth grade? So imagine I'm in eighth grade right now and I want to go to MIT. What would be your advice to me? And I want to be an electrical engineer and I want to be an AI scientist. And one more thing, Dr. Meyer, before we go on, let me just mention a couple of things. There are people on this call who are part of an organization I am partnering with in Nigeria called Giva. And Giva and Life and Sparkland, we're talking about how to transform Africa in STEM with STEM education. For those on the call, if you've ever heard of OpenStax textbooks, those free textbooks, that's Dr. Paul's advisor, one of his advisors. So we're talking to the person who worked next to the person who created these textbooks that African countries can use. So please keep that in mind. They featured our story. We'll talk more about that. So please, if you're on this call, you have access to a free chemistry textbook, free physics textbook, free math textbooks. There's a lot of stuff. And we should probably have a webinar about that too at some point, just to showcase what you guys did at Rice. But the STEM clubs from Giva and my organization, the goal of the club, Dr. Meyer, is this. Let me just explain the goal, and then you see where this question is going. There are places in Africa that don't have constant electricity. There are places that don't have running water. I want to fix both by God's grace. I want everybody in Africa to have electricity, water, healthcare, and what's the last one? Well, and security systems. But the point I'm trying to make, like I'm thinking of some things we'll talk about later. But what I'm thinking of is this. How can I inspire young people in Africa by partnering with other organizations to create STEM clubs that connect them to people like Dr. Meyer, who provide some counsel to the students who are trying to build solutions for their community? You see what I'm saying? So it's sort of a global connection. We had Dr. Colin Gan from Singapore this morning, and he talked about water. So we're going to deal with water. And there's another gentleman. But Dr. Paul, you're my guy for electricity and electrical engineering. You're one of my people. So we have to fix it. We want to use STEM clubs to do this. So there's an eighth grader or ninth grader. They're still young. How can we position them in such a way that they're solving practical problems and also getting ready to go to MIT or Rice? Do you see what I'm saying? Can you drop some projects for them or ideas?
That's a great point. And one of the if there is a silver lining to the fact that what you're talking about, that people in certain places in Africa don't have access to, say, water or internet or electricity, is this creates problems for future engineers to solve. And if you're, say, somebody in seventh and eighth grade, and this would be something to talk to some of these organizations that you're talking about, Amos. If we could just, even something simple like getting cheap Arduino kits to students so they can play around with programming hardware. And imagine, if you're somebody from Nigeria and you apply to MIT and you don't have the best, say you have decent grades and decent test scores, but what you're able to say is I developed a system, an electrical system that made the power in my village more reliable, or that allowed more people to get internet because we didn't have the resources that people say in America have. That's a really compelling application, and that's something that could be done very easily. Again, it starts with getting your hands on actual something that can be used. Obviously, if you're wanting to go more on the AI side, this would involve, say, getting your hands on some sort of computer and having access to internet. If you're wanting to be an electrical engineer and be on the more hardware side, this would be getting your hands on something that would allow you to prototype different circuitry. My thought is something like Arduino, something like a Raspberry Pi. These are relatively low cost things that can get you started doing that. AI, the thing that's difficult about training an AI system is it just requires so much compute. It requires so many resources in terms of computing resources, but that's not an insurmountable problem because one of the things you can do is you can learn to train AI on a cloud-based system. So you don't even have to have access to the hardware to be able to kind of to be able to do this, to be able to train an AI system. But again, I think engineering works better when engineers are closer to the problems that they're trying to solve. So many of you look around you and say, what is a problem that STEM could help me solve? And then how could what do I need to learn to be able to solve that problem? If your problem is electricity, then electrical engineering is a great place to go. And then there's going to be some resources on power distribution, and there's going to be ways you can learn how to do certain things with that will, I think, put you in a really good a good position there. AI, one of the problems with kind of modern AI is how wasteful it is in terms of water and in terms of electricity. And I kind of caution people from thinking AI is always the best solution to everything. It can do very well. It can do very well in terms of knowledge, especially if you're like, hey, like, what are some I don't know, like what are where are some places I can find schematics for delivering more reliable power? It can find good resources in that sense. But whether you want to be the ability to train AI on a massive scale, even I'll also put it this way, even at Rice in our research department, we had millions and millions of dollars for compute. We would buy computers, we would buy clusters, we would buy cloud, and even that couldn't hold a candle to what the industry, what Facebook and Nvidia, what they have access to Amazon to be able to do AI. So basically, AI research as like a research endeavor that's not somebody from Google. What we do in AI research, we just don't have the billions of dollars it takes to train a kind of state-of-the-art AI that does what something like ChatGPT would do, but that doesn't mean AI research can't make really good contributions. I think the contributions that come from research are much more about interpretability. It's much more about what are the limits of these things? How can we, from a conceptual place, make this better? And that's kind of an interesting point. Again, what you see, there are great people, really, really smart people from Google and NVIDIA doing research, actually publishing original papers. But it's these companies that have the massive compute and infrastructure that are able to really, because there's just scaling. You make the model, when we talk about deep learning, right? You're talking about the size of the model. You make the model deeper. A lot of times that just improves the performance because you have the more capacity to just store and glean more data from the internet. But I guess it's hard. I'm trying to think if you can find a problem that's local to you, that means a lot to you, because the more meaningful it is to you, the more you're going to be motivated to work on it. And then what Amos and myself and the people at OpenStax were helpful, what we love doing is giving people the educational resources they need so that they can solve those problems, so that they can say, okay, I realize that my issue is, say, electricity. I realize that learning electrical engineering will help me solve this problem. And it'll help me solve two problems. Problem number one is this problem that's local to me, say reliable power or anything. And problem number two is by solving this problem or making, like learning about this problem and doing something about it, it's also putting me in a good place to apply to universities and do this, because what universities will see is, oh, this is somebody not only who understands the STEM, but they're able to apply it to a real problem, which is something a lot of people in the US don't even know how to do. So it will really set you apart if you're able to not only do it, but then also talk about it or write about it.
Well, that leads me to, we're actually starting a journal. We're going to start a journal, God willing, that allows these, interactions with students to share what the, maybe I have an idea and I try it, and then somebody else in Zambia tries it, and somebody else in, you see what I'm saying? Because when we look at the history of science, and maybe we need to do that for a second, and then we're going to come back for one more intense AI discussion. I want us to spend a couple of minutes, if you can explain to people on the call how AI works in terms of a prompt to an answer. That would be our last AI nerd out session. And then, but here's what I was gonna say. So let's go to the history of science for a second. Let's use it as a chance to kind of drink some water, I call it. Let's just calm down. So you love philosophy. I was just telling people before this call that they need to take philosophy, that philosophy is good. And of course, mathematics is beautiful, but we're not going to go there. So looking at the history of science, who are your favorite scientists before 1900? Who are some of your favorite scientists and philosophers and mathematicians? Just give us a couple of names and why, and what you find interesting about them. I believe that by studying the works of the greatest scientists, it helps us have a better education. It helps us have a better, almost like you're getting some sort of encouragement from these people. They're dead, of course, but you can still find some interesting things to learn from their lives. Who comes to mind for you? Mine, by the way, you know already. I probably shouldn't need to say it.
Yeah, so like Amos, obviously Maxwell is a huge somebody I really admire. Isaac Newton, you can't go wrong with him. For me, the person that really that's come up a lot is Leibniz. And Leibniz is so interesting to me because I had been familiar with his work in mathematics. I mean, he along with Newton, they did calculus. What I didn't realize is Leibniz, how fundamental his theological beliefs were to some of his other. He's a very integrated thinker. You look at his thoughts, and he came up with the kind of modern binary system. And you look at what he was able to do, you realize his theology and his philosophy and his mathematics were all integrated. And that's interesting. And that kind of brings me into thinking of another point that I'll talk about here in a second. One of the people Leibniz was influenced by was Blaise Pascal. Now, I don't know if y'all know Pascal, but Pascal, when he was 19, he basically, I mean, he's also known as as an apologist, as a devout Catholic. He's a Christian, but he's also very well known in probability theory and in mathematics. But when he was 19, he built a computer, basically a mechanical computer, to help his dad, because his dad was somebody doing counting for taxes. And he saw a need, and he built this thing that could do addition and subtraction and some other things. And actually Leibniz, who eventually kind of became started out by actually building on to what Pascal had done. What Pascal made was something called the Pascaline. Very, very smart. The last name that comes to mind, somebody I admire, is Euler. I don't know if y'all know Euler, but he's one of the most prolific mathematicians of all time. I mean, just in terms of the output, he had a bunch of kids like you, Amos. And the story that my professors would always tell us, he was bouncing a baby on one knee and writing a paper with the other, because his collected works would fill bookshelves of mathematics papers. He wrote so much, and they think he wrote even more than is attributed to him, because he would have graduate students, and he'd kind of come up with an idea, and then he'd tell his graduate student, hey, like, work on this idea and publish it, and helping other people, other new scientists, kind of as an advisor to those people too. So obviously very, very smart. One of the things that's so important about studying the history of science is you realize how ideas develop. And one of the things, and this is a mistake I made, and I hope none of you here on the call don't make the mistake that I made, which is thinking that being a great scientist involves being born as this really, really smart person, and you either have this skill or you don't. Because that's not how it works. The way people become great researchers is they study a problem, they enjoy working on it, they look at the people that came before them, and they look at the needs of either their community or the new problems, and they say, how can I use what's been done before me to do something great in addition to it? Again, Claude Shannon comes to mind. He saw the relevance by studying mathematical logic of George Boole's results to these new ideas of digital circuits, of circuitry. Leibniz got started looking at Pascal's mathematical calculator and saying, how can I apply this to do additional like stepped division and other sorts of things? And even Pascal was like, how can I help my dad with his taxes? He's doing a lot of additions and subtraction. How can automation, and this is where AI can come in, how can that help with these problems that I have that are really near and dear to me? You look at the history of science, and it's very easy. One of the things that's challenging is you look and it looks like it's all these dead white men. And the only reason that's the case is because these were the people who were there when you had the institutions of science. If you're a woman or a man from anywhere around the world, you can be a great scientist. It just involves looking at the work people have done and applying that to your own community. So don't think that where you live or who you are or anything is anything that's going to keep you from having the possibility to do it. I think you can be a great researcher and a great scientist. Yeah, don't think that you have to be born with it. It's if you think that, you're gonna not study, you're gonna have the fear of doing it, and you won't end up actually diving in and doing the work that needs to be done to get you to that point to be the next Newton or the next Claude Shannon. These guys, they were brilliant, they were smart, but I think all of you here on the call have the capability to do that as well. It's just about really applying yourself and about finding those problems and then finding the resources, which I know Amos is working tirelessly at helping provide you with those resources, especially in mathematics, because that's what's really going to help to then apply that to the problems you want to solve, which is engineering. It's solving problems using basically mathematics is the way I like to think about it.
Yeah, and Dr. Meyer is talking to the young people, of course. There's also some of the teachers here. So, of course, I just wanted them to know that Dr. Meyer is encouraging our students. So, teachers and my friends on the call, you don't have to worry about the mathematics part, except you want to do calculus with us for fun. I'll introduce you to some other people on the call as we go on. But I left a chat. While there's a chat for you, a question for you, Dr. Meyer. While you look at that, I'm actually going to just make a couple of points. So if you don't mind synthesizing an answer for, I think, Alfred, there's a question that came in and I posted it in the chat. But while you look at that, here's what I want to encourage everyone to realize. The reason why Isaac Newton did what Newton did was because Newton had Galileo, Newton had Copernicus, Newton had Kepler. He had people that came before him. That's why he was famous for quoting somebody by saying, if I have seen further, it's because I have stood on the shoulders of giants. The list that I just put in the chat box, I say this with humility, but a great reminder. That list is literally all the key people, and there's more, but that's a great place to start. I mean, you got Euler, you have Newton, you have Pascal. Like, you can't go wrong. So if you know those people, like my kids sometimes joke that it's like, and my friends, they say like some of my best friends are dead, because these are some of the people I talk about all the time. Michael Faraday, James Clerk Maxwell. And so I bring all that up to say, please, teachers on this call, STEM club coordinators, and all of the people that are watching from everywhere that are just watching, please, we need to encourage children to know the people that gave rise to the ideas and these concepts, and then they need to take it to the next level. Dr. Meyer, we're planning to go to Cambridge from the 9th to the 16th of August next year with some of our students and teachers. And so I bring that up now because I want to show them where Newton was. I want to show them where Maxwell was. But anyways, I'll let you answer the question and then we start landing our plane in the next few minutes.
Yeah, so Felipe is asking, he's doing an undergraduate in mechatronics engineering, and he wants to know how he can integrate using AI while using IoT. So he's working on IoT and embedded systems. And his concern is by trying to learn multiple things, you end up not mastering anything. My thought is AI is such a broad field. And in my view, IoT is a little bit more narrow. One of the things that isn't a bad project. So think about, is there a project you can do that will allow you to kind of learn both or understand both. So the first thing I would say is learn embedded systems on a fundamental level. Find a good textbook. I mean, if you're an undergraduate, so I'm thinking of like I was thinking of really introductory books, but you're probably beyond that point. What comes to mind is there a project you can work on that will allow you to understand AI and embedded systems at the same time? Like, is there a way you can look at taking an AI model that's trained in Python and writing it in and converting it to C so it can run on an embedded system? And this is a project that you challenge yourself, oh, if I do this, I will not only be learning embedded systems better, but it will allow me to also understand AI a little bit better. And that will teach you AI from a very fundamental place. If you can take an AI model, even if it's a basic one, like the basic MNIST digit classification, classifying digits, that's an easy thing to write in Python. I mean, there's like scripts you can find online. If you can take that and run it, find a way to run it faster on an embedded system, you're not only learning, you're forcing yourself not to just learn embedded systems really well, but to learn how AI is run on the hardware. And that will make you a better embedded systems engineer and a better AI engineer as well. With that being said, if you're not interested in learning how to like train AI, if you're just like, how can I integrate using AI while learning IoT and embedded systems, that's also an option. So it can be, say, I'm working on an embedded systems project and I can be prompting AI for help when I get stuck or when it comes to, hey, I'm having trouble understanding this concept in embedded systems. Um, like what can be the causes of an overflow error from, I don't know, or like, the watchdog timer is doing this. There are concepts there that I think prompting AI can be helpful as well. But if you're really wanting to learn AI, I think it's good to go through and to learn to train your own models. And then if you want to apply that to an embedded systems design, there are ways to do that with a project that I think would be very, very interesting and a way that I think, again, I think you can even make that a good case if eventually um, you're looking at going to applying to, oh, you're already in as an undergraduate, but yeah, for
Maybe
people who are
graduate
applying to
school.
colleges, there can be cool ways to do that. You can say, here's a model that did this. We didn't have access to the compute or resources. So what I did is I took this model and I trained it on an embedded system and we only got 40% of the performance, but it used 10% of the power or something like that. That's really compelling. That's something I don't even think a lot of undergraduates could do. So if you're seventh, eighth, ninth grade working on something like that, again, it's going to take time, it's going to take work, but these kinds of projects are going to be very fruitful, both for your education and for eventually applying to universities and things.
Yeah, so Dr. Meyer, one idea that just dropped in my mind is that maybe our STEM clubs can talk to you about compute later, about how to, deal with that. So there's something cooking. I'm not going to go into too much detail here so nobody steals my idea, but I have an idea we should talk about. By the way, Dr. Paul Meyer and I live like next to one another in city-wise, but we keep missing one another. So I just thought, why don't we just do this? And then the other questions for Dr. Meyer. Before that, I have some rapid succession questions. What books have you either written, contributed to, or are working on writing right now related to math or anything?
So the big one that I've kind of have a draft on very early, it's already hundreds of pages, but is mathematical logic for STEM. So this is taking the ideas in mathematical logic, trying to teach philosophy, or the thinking part, coding, and then aspects of mathematics all at the same time. So I do examples in Python coding, but then also trying to teach kind of the thinking side of it and logical arguments alongside. So that's the big one. In addition to kind of my thesis and other kind of more technical papers that I've been working on or continue working on as well.
What's your thesis?
My thesis was called Rethinking Maximum Likelihood Estimation. And basically, what it was one of the things AI struggles with because it's not trained to do this is what we would call cognitive metacognition. It's me thinking about my own thinking and quantifying how confident am I in my own belief. And there's a way you can take an AI system and you can kind of force it to quantify, hey, how confident am I that this is the correct answer given the data that I have? And you can basically, there's a process of training it and it ends up being more stable in certain scenarios and it ends up I guess, preserving the overall data more. So that was kind of my overall thesis and different ways to do that. And that brought me into interpretations on probability. So there's a great chapter in that book that is a paper I'm hoping to get published in a faith and philosophy journal on how this interpretation of probability makes belief in miracles rational, because you sometimes hear that. And it's, I mean, it
Okay.
gets to be, it's very deep. You start pulling one thread and it's like spaghetti, you start
Wow.
realizing it's all connected to these different things. So that's kind of, those are the main projects I think I'm working on now with those papers.
Okay, and then we'll need your YouTube channel too, so we could share that with people later. The channels that you have, great stuff you are putting out there. You have videos on math, you have videos on some explanations, right, with signal processing. So if you don't mind, just maybe later dropping those in the chat as we wrap up. What computer programming languages do you work in?
So if you're doing AI research, all the AI researchers use pretty much Python. And the package that tends to be used more by research scientists is PyTorch. So PyTorch is a version of Torch, which is a deep learning neural network AI library that's done in Python, hence the PyTorch. It was originally in a different language. So learning Python is also a programming language that's taught at introductory computer science classes. It's really a good place to start if you're wanting to learn programming because it's very similar to English. The syntax is it's a little bit easier to master as opposed to something like, oh God forbid, assembly or something like that. Yeah, so Python, and then if you're trying to get into AI, PyTorch, it's really easy to find tutorials and resources online. The other one would be TensorFlow. That's kind of the one that Facebook's using, but I personally, and again, I'm biased because I'm more familiar with the research, I would say to start with Python and PyTorch. There's some good tutorials out there if you're wanting to learn about AI, learning how it's trained, things like that.
Okay, no problem. So for this is for my video recording tracking. So we're gonna teach Python to everybody, and PyTorch, and then we could have a TensorFlow on the side. Dr. Meyer, we'll probably have to have a nerd out webinar session where you can go all out on your thesis and just go all out on this discussion. So please stay tuned if you guys want to go into those kinds of conversations. Make sure you have a good breakfast, make sure you rest well the night before, because it's gonna be intense. And then the other thing, the STEM clubs, I'm just thinking about your book that you're writing. Would you like to maybe look at talking with some of our coordinators to talk about how to have people try it out, in a sense, in the communities where these are, basically like, here's a chapter. You guys want to read it and give me feedback. I think that there will be people who are even in 16 to 18-year-olds, so they should be able to handle some of the content. How young do you think someone could be to understand what you're writing in that book?
That's a good question. I think it could be like 10 to 12. Maybe 12 would be a good minimum.
Okay.
Again, this isn't assuming any background knowledge in programming, and it doesn't assume that much background knowledge in philosophy. Again, it would be good. My goal is this book. I want this book to be free. I also started a YouTube channel to try to teach mathematical logic, and I kind of put that on hold to write the book first. But that's another way where a lot of the content is kind of shared between them. I'll see if I can find that and put that in the chat as well. I started that last summer and then was getting into the time of really writing my thesis, so that didn't go to I didn't go as far with that. But again, I want to offer the book for free, and I think it would be a really important way to learn programming and to learn mathematics and to learn some philosophy. It wouldn't be a super it'd be more the analytic mathematical logic part of philosophy, but still how to think about constructing arguments and things, which are really important. When you think
Yeah.
about guys like, I'll just say this, Newton and Leibniz and Pascal, they all had a background in this sort of classical education where they would have learned logic and rhetoric. So keep that in mind too. I think our education system, at least in the US, has gotten away from that, and I think it's a little bit to our detriment, to be honest.
Yeah.
But
Well, it's coming back. Classical schools are growing. And honestly, one thing I said, there's a question for you in the chat. But one thing I said is that classical education is probably the only form of education that can survive AI right now. Because AI destroys everything else, in the sense that if your goal of your education is just to pass tests, or if it's just to gain knowledge, AI is there, and whatever, that's just not going to be sufficient. But classical education calls you to think about how to learn. That's going to be critical. So what are your thoughts on the question? Someone asked about Gen AI standards.
So that's an interesting question. So do I think that Gen AI standards are too lack of standards? maybe who asked that if you could provide a little more context. By lack of standards, you mean lack of standards in terms of creating the model, lack of standards on content that's being generated? I guess I just want to make sure I'm understanding exactly what is meant by that.
Well,
Um,
there are many Gen AIs, right? You have Chat GPT, you have Claude. I can go out and maybe get some money and start one too. Do you see what I'm saying? Where do we draw the line of like who's is the market determining what AI apps are going to succeed, or is there anybody else regulating anything?
So yeah, that's part of the thing. There's currently there's very little to no regulation. And one of the really interesting reasons you don't see that is it becomes a jurisdiction issue. And these companies have found ways to get around it. Like Facebook can say, oh, our AI lives in a server in this other country. So do copyright laws, say in the US or some other country, really apply if where is the data, right? It's in the cloud, but it's stored on some server in some physical location. But what happens when it's distributed? What happens when part of the model lives here and in this country and that country? So I would say the big problem I see coming with Gen AI is a lack of really consistent watermarking. So knowing that something is AI created, I mean, you start thinking of what if you make an AI video and you look at some of these like Sora AI can generate videos and other things of some politician saying something that he didn't actually say. How do you know he didn't actually say it? So one of the lack of standards of watermarking of just saying this is a video generated by AI, and then if it's coming from a camera, it's like this is a video that was recorded from a camera. The actual like stamping process, a lack of standards of that, I think, is the most concerning part to me from just a social perspective. But I think also, yeah, like it's not a bad thing. I think that you have Chat GPT and you have Perplexity and you have these other AI systems because I think that competition does breed innovation to a certain degree, but then you start wondering innovation at what cost? You know, is there a cost to artists? Is there a cost to other things? So I think the lack of standards that I think of is a lack of standards on watermarking, a lack of standards on copyright. Like these AI models are being trained on these textbooks and the people who wrote the textbooks aren't getting any royalties, and yet these AI models are able to basically verbatim spit out a copy of chapters of the textbook and things like that. So yeah, I would say the lack of standards is really it's hurting people more than it's hurting AI, but it's a very significant problem. And that gets to be an interesting political issue. And that's an area I'm not super well versed in, but how could you regulate it? What would be the safeguards you'd want to put on it? And then if so, how can you do so? I'm talking with a few people in 2 weeks. We're having a kind of a forum on looking at that. But
Yeah.
yeah, it's a very interesting issue.
Well, I think that one of the meetings we need to have in this fireside chat is I'm going to bring in a political scientist or somebody who is more in the regulation side, and let us have them. Let's grill and see what happens. So please, everyone, stay tuned for that. Three last questions, Dr. Maya, and then we're done. They're not too long. The first one is going to be how does AI work? Can you keep it to layman's terms as best as you can in terms of how does AI work, if that makes sense? So that's number one. And then I'll let you answer that sort of. Again, I don't want people to like get lost in the math and so on, but how does AI work? And then I have a couple more and then I'm done.
So when we think of AI, what I guess
Oh,
there's a
Gen
lot of
AI, sorry. That's
yeah.
what I
So,
meant.
so Gen AI, what I'm thinking too is like maybe I'll use LLMs as an example, but AI in general is what we would call an artificial neural network. And what that is you take some input, and it could be an image, it could be a text. You do this process of what we would call tokenization, or basically you convert it into a set of numerical values. And then what you do is you do what we would call in linear algebra matrix multiplication. So you basically do multiply two numbers and add, and you multiply two numbers and add. And then you add another number on the end, and then you apply some really simple function to transform it, and then you get some result. And then what you do is that what we call the deep in deep learning or deep neural networks is you do that a lot of different times. So you do the multiplication, you get a result, and then you do another set of multiplications and do that. And what ends up happening is you get some output. Now, the way you would train the model is you can think of those numbers that you're multiplying by as like knobs, and you can kind of very so slightly turn the knobs a little bit. So if I'm having a Gen AI and I want it and say I'm think of like ChatGPT. What you want it to do is you want it to predict the next, you want to train a model to predict the next word in a sequence, like in a sentence. So you give it a lot of text where you know what the next word should be. And you say, here are the first 10 words. What should the next word be? And you run through and you start, the whole thing is completely random. And it spits out some number that corresponds to a word. And it says, this is the word. And what you say is, no, it actually should be this word. So tune all those knobs ever so slightly so I get a little bit closer to the word I want it to be and not this random word that you put out. And you do this billions and billions and billions of times, ever so slightly tuning these knobs as you give it more and more text. And eventually it kind of learns to try to output the word that it thinks is next based on the context that it has. I mean, that's really what it is. It's matrix multiplication and then some way of converting text or images into numbers so you can actually do the multiplications and transform it back. I mean, that's literally what AI, all of AI
Wow.
is. This is why you got to learn math. This is why you got to learn math from Amos.
Thank you so much. Wow, that just left me going, okay, I don't even know my other questions anymore. That was good. We're going to do a video where we do some math problems on a board. So maybe we should find a spot in Austin. Please run that. Lastly, so AI software and hardware, how are they working in tandem? Because technically everything you described could be happening, but be very slow. But now we know it's very fast. So where does NVIDIA come in with, how does that all fit in? Hardware, software, and then we can land our plane.
That's a great question. NVIDIA, they got started. I actually knew a guy who one of the guys I worked for the founder of NVIDIA, and the guy offered him to be an early investor at the time, and he didn't take it. And he's the biggest regret of his life because one of his friends who took him up on it now is like retired at 40 and like has his own island. But NVIDIA got their start making graphics cards, doing graphics processing for computers. So you think if you ever play a video game or any sort of 3D simulation, what you're doing is you need to do a lot of computations in parallel, which means at the same time, you're doing a lot of mathematical operations, but you think about rendering a 3D scene, each pixel, you think we're transforming objects in 3D. These can all be represented by rotations. And again, there's a lot of mathematics in that. So NVIDIA developed their hardware to do graphics processing, which was doing a lot of things in parallel and doing a lot of mathematical matrix multiplications in parallel to calculate graphics. And the smart guys at NVIDIA said, well, this would work really well for AI as well, because guess what? AI is also a bunch of matrix multiplications, a bunch of multiplications in addition that can be done in parallel, both as you're trying to predict the next text and also as you're going back to update the other things. So the AI hardware, what you need, and nowadays you have GPUs, your graphics processing units, and that's very similar to what you would call a TPU or a tensor processing unit or an dedicated AI hardware. So the demands of what the AI system needs to do will inform the hardware that you design, but luckily there's hardware that's there. Then of course, people designing AI say, what I'm slowed down by is my inability to process data. How can I leverage existing hardware to make it possible, make it even feasible for me to train this within my lifetime, to do the kind of knob turning that I was talking about there. So you kind of see this, software people see hardware and they say, I have this need in software. How can hardware kind of fit in? It's an engineering problem. So they do that. And then the hardware people say, hey, these software people are doing this. How can we design hardware so that we can make their life easier? We can do this thing that they're doing faster. So they make this improvement. And then the software people, and sometimes they're the same people, are like, well, wait, that can also be used over here. So there's kind of this back and forth. So they kind of both try to meet the needs of each other. But really what you need is for it to be reasonable to do this, especially as you scale up, as you get to these billions and billions, if not trillions of parameters, you just need more compute. And that's where that dedicated hardware comes in. And that's where you can use, if any of you have a computer with especially an NVIDIA card with a graphics processor, look up CUDA. It's CUDA, and it's their way of using existing graphics cards to do neural network AI training. It was funny, like our lab, we had a bunch of graphics cards, and we never used them to play games, but you could probably play some really high definition games if you wanted to on our lab machines, because it's all these GPUs in these boxes, like running.
Wow. we need to do what you see. I'm writing it down. How to train AI models. We're going to talk about some of that in one of our fireside chats. Last question that came in, and just the last two. You talked about the future. You were going to talk about the future a little bit. Like, what do you see for the future? But someone asked, since nothing is permanent, project what replaces AI in 7 to 10 years. What do you see the future of AI and that space? Can you answer that if you don't mind?
Ooh, that's a good question. What I'd like to see, what I think is gonna, so typically what you see whenever there's new technology is there's this initial hump, there's this hype curve, and it kind of gets overhyped, and then it either stays as a kind of mature technology or it kind of dies out because something replaces it. But this is kind of, everyone puts their whole thing in. And a good example of this was like the internet. Back in the 2000s, there was, and this was when I was too young to remember, but there was this thing called the dot-com bubble or the dot-com boom. And these companies were hiring people who could program, who didn't know programming, but that's because this was what the big hype was. Obviously, the internet is now a mature technology, and it's become a part of most of our lives every single day. So I don't see AI in its current form being replaced. What I think you're going to see is an versions of AI that are able to capture long form content. As you can store more with memory, right now AI can struggle with causality because it's given data that has zero context. It's like, here's a clip, here's an image, here's this. How do you get continuity? Because you need that continuity to understand, oh, this ball hitting this object causes it to topple, and getting a kind of an understanding of different things. So what I see again, and what the buzzword you'll often hear is multimodal, which is the idea of AI that works with text, image, video, and audio all together. And this is where that signal processing comes in. They're all signals, they all convey information. What can a system glean from this? I don't believe in AGI or artificial general intelligence. To be honest, I think that's a myth. But I do see what we would call AI maturing as a technology. And then what would be the thing after that, I think, would be having AI. Perhaps it would be learning to use quantum computing to train AI. I think that would be quantum computing, and then also quantum computing for quantum materials would be the other thing, where it's, again, you're not limited by this kind of really sequential aspect of it. I think at a certain point, if we can figure out how to use quantum materials and quantum computing, that'll totally change the way we have materials. It'll totally change computing, but it will also change other things.
That
Um,
makes sense. And I was going to tap two of my advisors, but I won't distract them now. But if they want to share, they know more about the dot-com bubble. When you mentioned that, I thought about them right away. One thing I do want to ask is, have LLMs hit a wall? Do you feel like have you sensed? I'm just saying, like, are we at a certain? We've ramped up. We've got to this point, and I just feel like a lot of the models now is not too different in one sense in some of the quality. Do we just need a new paradigm to sort of push the AI to another level? And they do talk about AGI. We'll talk about the problems with that next time. But what are your thoughts on the LLM limits?
I think LLMs have hit a, or there's what I would call, yeah, like they've hit a wall or they've hit a saturation point. One great example of this in compute is we have the idea of Moore's law, which is every so often, maybe 18 months, you the transistor size on the gate of a computer you can half it, basically get smaller, you get more power efficiency, you get more speed, and you do this. Well, there's a limit to how small this can be shrunk, but computers have been able to get faster using other tricks and other things. So I do think LLMs have hit a wall because what it was is there was a very clear path forward. It's we need more data, we need a bigger model. The problem is you get to a point where more data isn't going to solve the problem. I think LLMs have hit a wall, and one of those walls is insurmountable. It's just the fact that it's given all these tokens and it's given text, but it has no context of what this text refers to. There's a really interesting thought experiment by philosopher John Searle called The Chinese Room. I encourage everyone to look at that and look at this is something he came up with in the 80s before anyone even knew what an LLM would be like. And it's still relevant to where one of those walls of LLMs. And I think that's an insurmountable wall, to be honest. Where I think there are other walls in terms of performance right now that LLMs can get around, and that's and could be partially with that. It's understanding the context that the data is presented in a little bit. And I think if you're able to give, for instance, a context of reasoning, if you're able to improve the LLM's ability to do any sort of abductive reasoning, deductive reasoning, yes, but abductive reasoning, where it's kind of has different hypotheses and tries to pick the best one, if it can kind of quantify hypotheses and act on those hypotheses. Again, this is all artificial, but it's something that I can conceivably be programmed, programmed behavior. I think that will allow, again, you're still going to have a saturation point, but I think that is not an insurmountable challenge. And I think that will be the next breakthrough in LLMs, is to get that sort of reasoning, taking, operating well.
Wow. Wow, thank you so much, Paul. I really appreciate it. And there's a lot more we'll talk about soon, but I know you have to go. I know people might have to log off too. So thank you for the YouTube channels. We would love you to talk more to, some of our STEM people. And so, please, we'll keep in touch. And maybe one of these, we can even be in the same room and have a podcast style.
Yeah, we could have the chairs and everything.
The chairs, I know. Look at that. We're growing up. Okay. Well, look forward to it. Well, thank you so much. I'm actually in Houston right now, so I might be passing Rice University. So anyways, I'll wave to Rice as I drive by. So, but thank you so much, and everyone on the call, thank you for joining us. There was a lot to chew on. If you're going to get into top universities, you need to understand AI. That's just a no, like in terms of just the world you're living in right now, what's going on. And Dr. Paul Meyer is going to help us better understand things. Let's look at his math videos. Let's look at his textbook when he sends it out, or samples, and help us. I'm doing some of this work. What I mean is help us think creatively about engineering in such a way that even though people live in Nigeria, we are learning what people in America are learning and how they're using those tools. And we start building our own cloud systems. We start building more. That's what I want to see. I want to see AI scientists come out from, lots of them from Africa. So we will be talking very soon, Paul. Thank you, everyone, and have a blessed day. Any final words, Paul, or should I just say goodbye?
I'll say again, thank you so much, Amos, for having me on, and great to chat with you, and thanks for the awesome questions. I'd love to be back, and I'll hit Amos up with a few of those resources that I recommend too. Some of those papers, if y'all are interested in learning a little bit more, and I'm very much on board. Would love to see the next big AI scientist come out of Nigeria. So I think it'd be awesome.
No problem. And those who are from other African countries, no, don't worry. We're doing it. There'll be more. They'll be coming from all over Africa. And the US too, though, Paul. I want to help in the US, but I don't see kids who want to do calculus for fun enough. I need us to wake up. We got to wake up if we're going to lead. And that requires calculus early. So when they're ready. Thank you, Paul, and have a blessed day.
Yeah, you too.
Take
Thanks.
care. Bye.